So thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Alexander Dalzell from AWS Center for Quantum Computing. And he will tell us about a distillation teleportation protocol for fault-tolerant QRAM. So Alex is a senior scientist at AWS, leading the quantum algorithms team. His current research interests include quantum algorithms for linear algebra problems, quantum classical simulation of many body physics, and opportunities for co-design between quantum algorithms and fault-tolerant architectures. Before joining AWS, Alex did a PhD at Caltech, where he worked on the complexity theory underlying random circuit sampling experiments. So Alex, the floor is yours.
Great. Yeah, thank you. Thanks for the invitation. And yeah, I'm excited to talk about this this paper with you guys. It's based on joint work with a number of other people listed here. And all of us sort of had or have had an affiliation with AWS in some capacity, the AWS Center for Quantum Computing. So this work kind of came out from there. And yeah, hopefully you guys can, interrupt me if you have questions along the way. I think it'll be, 35, 40 minutes, hopefully. But yeah, we can skip a few of the slides if needed. So yeah, let's get started. So the topic is quantum random access memory. But before I talk about QRAM, I want to talk about normal classical RAM. We're going to have a very simple model of RAM to kind of focus on the fundamentals here. We're going to imagine that we have n address bits, and at each of the 2 to the n addresses that these address bits index, we store 1 bit of data, either a 1 or a 0, which we can organize into a table such as this one. And the random access memory operation is simply to, upon receiving input x, retrieve the data item f of x stored at that row in the table. And this is an operation that we often kind of take for granted in the analysis of classical algorithms. We make this kind of cheap RAM assumption, which is that the cost of performing this memory access operation is only polynomial in n, or even sometimes we kind of assign it unit cost. So even though the memory has size 2 to the n, we want to be able to retrieve a data item in only poly n time or cost. And this is kind of borne out in practice because we can actually build these super efficient RAM chips that actually kind of can quickly access data that's very, very large. So this assumption is needs to be realized in practice to kind of to make sense. So I guess naturally we've tried to generalize this concept to quantum computing, where we have quantum random access memory. And here the setting that I want to think about is where the data itself is still classical. We still have a fixed static data set, the same as before. What changes is that the input address can now be a superposition of many of the addresses. And we would like to preserve that superposition and kind of attach the value of the data to it along the way. And kind of the simplest version of this is this phase QRAM, where all we want to do is apply a -1 phase onto basis states corresponding to values of x where f of x equals 1. As an example, if we put in this superposition of 4 addresses, we would like to just flip the signs on 3 of the 4 addresses, right? And it's not necessarily common, but it's something that people do sometimes is make this cheap QRAM assumption, which is just trying to mirror what the classical algorithmic analyses are doing and say, okay, this is basically the same as classical RAM. Let's just assign this operation cost polynomial in n, even though there's an exponential number of data items. Of course, you can kind of see that already it's a bit weird because with just a single query to this QRAM operation, we can kind of access all of the data entries in some capacity, right? We can put information about all of the data items into the superposition with just a single query, which is kind of something we couldn't do with normal RAM. So we'd like to interrogate this cheap QRAM assumption in this talk, and hopefully make some progress on justifying it, but also understanding its limitations. But before yeah.
Sorry, can I just interrupt with a very basic question about the model? I guess right now you have f of x is just a bit, but if it was a bit string, I guess you don't necessarily want to, call each bit of the bit string separately. Maybe it's quicker to, I don't know how classical works. Like, is it quicker to call the whole bit string rather than calling it like k times for each bit, like k times for each bit?
It's a good question. Yeah, and so in classical RAM, they heavily, often when you're looking for data at a certain address, you want more than one bit stored at that data entry, and kind of often you need many bits. So it is possible to generalize this to where there's like b bits stored at each data address, and then in the kind of classical case, it's sort of clear how that would generalize. Where you're just receiving multiple bits. In the quantum case, it doesn't quite work with this phase quite as easily, but you can still make it work. And in kind of the appendix of the paper, we actually talk about this. But you would just append another register, and you would want to read in the value of f of x into that register, and then you can kind of you can make this into a phase. Essentially, this phase version, the single bit phase version, captures the essential complexity for the purpose of this talk. But I can maybe make you feel less worried that it is possible to generalize it. Yeah, does that help?
Yes.
Yeah, okay. Okay, so I guess before I explain the technical aspects of our protocol and whatnot, I would like to kind of convince you that this is important. That this is kind of a really pressing question for quantum algorithms. And that's because a lot of quantum algorithms have been proposed that make this cheap QRAM assumption. So if the cheap QRAM assumption fails to be true, then like a whole area of quantum algorithms becomes, still potentially of academic interest, but like completely irrelevant for practical quantum computing. So we would really like to know whether it's true and to understand its limitations. Just as some examples, right? There have been many of these quantum algorithms for various learning tasks in like quantum machine learning, like linear regressions, support vector machines, things like this, where we have a large matrix of classical data and we want to perform some kind of linear algebraic manipulation of it. And all of these almost always require this cheap QRAM assumption to be able to access all of that data in superposition if we hope to have a exponential or even, oftentimes large polynomial speedups. Another example, which I think is underappreciated, is solving differential equations, which is another area that has been proposed for quantum algorithms, where in real practical engineering workflows, the problem instance itself is usually specified by some complex like boundary condition or something like this. And if you want to have a quantum advantage in these situations, you would like to at least be on equal footing as the classical algorithms and have this cheap QRAM assumption be true. Because often we're assuming the cheap RAM assumption already. And then also these quantum algorithms for like linear programs and semi-definite programs. In practice, these linear programs and semi-definite programs are stored in memory somewhere. And so we want the quantum algorithm to work. They also need to be able to access that memory, but coherently with cheap QRAM. There are also some examples where it would be nice to have cheap QRAM, but it's not necessarily essential for a quantum advantage. So if you think about like quantum algorithms for chemistry, where we might write down a list of coefficients for our Hamiltonian in classical memory, and then we want to do a quantum algorithm. Right now, the way that those algorithms are usually compiled is this quantum read-only memory circuit, which is just like it goes through the data linearly. So if the data has size 2 to the n, it pays the full 2 to the n cost to access that data, and it still manages to get some argument for quantum advantage. So it would be really nice if we could actually improve that data lookup cost to only polynomial in n rather than 2 to the n, and might improve the outlook for these chemistry algorithms, or for some algorithms with like Shor's algorithm. Actually, the modern compilations are also doing this kind of table lookup operation. Yeah, so cheap QRAM is not necessary for these applications, but it would be nice. So yeah, hopefully, I guess you're somewhat convinced that this is an important question. Now let's talk about why it's a hard question. So just a reminder, right? We want to perform this unitary, which we call V of f, where f is our data set, which maps a superposition to the same superposition with the phases attached to the basic states where f of x equals 1. If we want to justify this cheap QRAM assumption, one way we could do it is to compile that unitary into a shallow quantum circuit. And this is achievable. You can write down circuits which have polynomial in n depth. In fact, you can have linear in n depth. But of course, the cost of this is that it requires an exponential number of ancillary qubits and total gates. But so far, this is the same story as for RAM. In normal RAM, you would also have a hardware object which had an exponential number of gates, but only a linear depth. And we know that normal RAM is possible. But it gets a bit trickier when you try to think about how noise interacts with this circuit. Like, how would we make this circuit fault tolerant? The way we normally make quantum computations fault tolerant is to apply the methods of general purpose universal fault tolerant quantum computing, where we take each gate in the circuit and each qubit, we encode it into a quantum error correcting code. We use fault tolerant gadgets to perform those gates, and so on. But when we look at doing that for this particular circuit, we run into some problems. So first of all, the total number of gates is 2 to the n, and the total number of non-Clifford gates is at least square root of 2 to the n. This is a hard lower bound. And we know that these non-Clifford gates are difficult and require techniques such as magic state distillation. We also know that just to keep this whole circuit fault tolerant, we're going to be having to do quantum error correction on all of these exponential number of components in parallel. The way we imagine doing quantum error correction, usually it's very active, right? We're kind of doing measurements on the system, right? If the total size of the system is 2 to the n, it's not very plausible to say that the cost of this operation is only polynomial in n. It contrasts quite starkly against classical RAM, which is kind of a very passive operation that just you build the chip, and then the chip just does the operation without any interventions required. And I guess just as like a quick small calculation, if we imagine we have a 100 kilobyte quantum RAM, and we encode each of these ancillary qubits into a surface code of distance 11, and then we operate at a clock cycle time of 1 megahertz, which is kind of what we normally assume for superconducting architectures, we would conclude that this whole operation requires 1 million logical qubits, 200 million physical qubits, and meanwhile, it's generating 15 terabytes of syndrome data per second just to kind of perform the error correction. So this is a pretty large-scale operation just to perform a query for a 100 kilobyte QRAM. It doesn't really pass the smell test, you might say, that this is a cheap operation that could be considered on par with a 100 kilobyte call to normal classical RAM. Yeah, the point of this slide is just to kind of point out that performing quantum RAM in a general purpose fault tolerant way is not a very effective idea. But yeah, I'd like to kind of pause here for a second and see if anyone has questions about this this kind of line of argument, because I think it's a subtle thing that is central to this work. Okay. In that case,
sorry, Alex. I mean, I think I have a question, but I haven't really formed very well. Like, I guess, we need 1 million qubits, logical qubits, to store this data. But I guess that, I mean, what kind of, we kind of trying to do what we would do classically. Like, we're trying to kind of think about like a classical computation. If you try to do it, with quantum, you need QRAM, and you need some ridiculous amount of logical qubits even to do this. But realistically, we know qubits are very expensive, and we don't, we wouldn't try to do some classical operation like this. I guess I'm just asking the question, like, what is the model in which, QRAM is really necessary? Like, of course, we could think of like situations where the info we need to use is computed, like say in there's a situation where the f function is like a database, and you just kind of have to store it, and that requires a whole lot of pre-computation to load stuff into QRAM. And then there's the situation where f is an actual function that you could compute with a quantum computer.
Oh, yeah. Okay, good question. So is this strictly for the situation where f is like the first case you said, where like f is an arbitrary function that it stores data that we've collected from experiments, or in chemistry, right? You compute beforehand all these coefficients, and you just have them, and you need to like read them into the algorithm. But there are other examples, and sometimes you can formulate these chemistry algorithms to like compute f on the fly, we say, where like f of x is not an arbitrary function. It has like a closed form in terms of x, and we can compute it in polynomial time. Like this is common, yes. But I guess, like when you're thinking about like the differential equations, like the description of the plane is like something you inherently have to store in memory. You can't like compute it on the fly. Like maybe you can if you break the plane down into like a cylinder with like a cone. There could be like a very small number of like parameters, and you could compute from those parameters the value. But yeah.
I guess my question, what I was trying to get at is like, I'm trying to understand, like, say in this example, not of the plane, but of this the linear equation problems. These are like stuff where you're loading the information in, for this B vector or something. Is that right? Rather than having it computed on the fly.
Yeah. So maybe you've loaded in B. I mean, like. Or certain entries of A are kind of stored in memory. I mean, if you think about many of the applications, of this in practice, like, in machine learning, A is like a gram matrix. It's like a bunch of inner products that you've calculated or something, it's like a big data thing, right? Or if you think about just the way like neural networks work, right? Like we're storing the weights of the neural networks in memory, and there's no way to compute them on the fly.
Yeah. I mean, I kind of understand the application. There's like kind of crazy applications from finance and stuff where people think about like loading in like all the portfolio data or something for like portfolio optimization. But like, I guess what I'm trying to get at and understand is like this question of efficiency and the ability to do this in polytime, and how that applies in this setting where you have a database. Like, I guess I don't understand what kinds of problems the database would scale. But it's a fixed database, not a function that you're computing that populates the database. I'm a little confused about this. I don't know if you have anything to say.
I guess we worded it in terms of a function, but I think I was thinking about functions and the database and the function is like interchangeable for this talk. Like the function is just a way of writing the database, but the database is arbitrary. So we're really talking about databases here, not computable functions. Like the function is not computable.
Yeah. At least not in polytime computable. Yeah.
Yes. Yeah.
Like the way to think about it. Yeah.
Like there's a doubly exponential number of functions. Like each of these 2 to the n entries can be a 0 or 1. So there's 2 to the n different functions, and our like method will work for all of them equally well. It's agnostic to which one you're looking at. It doesn't utilize any structure. If there is structure, it could be very inefficient, but its generality is its strength.
Yeah. Okay.
Yeah.
Mm-hmm.
Okay. Maybe we can return at the end to some of the like philosophical like aspects of this, because I think that's an important aspect of this work, is like the conceptual. What does this mean? Why is this important? Okay, so we talked about why this circuit QRAM is not a good way of justifying this cheap QRAM assumption. What we'd really like is a different approach where we perform this QRAM operation in a specialized way. So we don't use like the methods of general purpose fault-tolerant quantum computing. We have a physical device which is hard-coded, it's specialized to do QRAM. The same way we do classical RAM, right? The classical RAM part of your computer is different from the CPU. We build that thing to do RAM. Why don't we build a hardware device that is specialized to do QRAM? And we know that this device would be noisy because we can't control quantum hardware well enough to do perfect hardware, and it would perform QRAM at the physical level. So this is like more defensible that you could come up with this, although this is also a hard problem, how to come up with a good experimental proposal. And we might ask, let's say we had this. Let's say we had a black box which performed noisy physical QRAM. How would we make that fault tolerant? As a brief aside, this would be an easy problem in the classical case, right? Let's say we have a noisy RAM, which means that we give it an input, and then it gives you an output, but it flips the output with some probability, right? So for example, we give it input 101, it should give us back the answer 1, but sometimes it messes up. We can easily make this fault tolerant with a simple repetition code, right? We just do it many times and we take the majority vote. And if we do it enough times and the error rate is low enough, then we can return the correct answer. So this is a pretty easy problem to solve on the classical side, but it doesn't work for QRAM. And the reason it doesn't work is that the repetition code, right, it doesn't protect against phase flip errors. And phase flip errors would decohere the superposition, right? An important requirement is that we preserve the superposition that we input. We can't reveal to the environment which of the addresses we are actually querying. We have to preserve that superposition. So this repetition code doesn't work. And in fact, you might ask, like, maybe there's another code that we can use for which QRAM is transversal that could be used to do this kind of trick quantumly. But it turns out we have pretty kind of concrete evidence that all the codes for which QRAM is transversal have an exponential number of bits in the length of the words. So like this is also maybe a not going to work for QRAM. But this is like sort of the goal, right? The goal is that to assume we have this black box which is faulty that does QRAM and try to figure out a way to perform QRAM at the logical level. And that's, I guess, the main contribution at the technical level of this work. So we give a protocol which assumes that it has access to a physical QRAM device which has a small but non-zero correlation with the correct output. So like on a certain input, the device might make an error 99% of the time, but it preserves like 1% correlation with the signal that it's of the correct output. So we assume we have this black box device, and we also have a fault-tolerant quantum computer. And our protocol uses both of these ingredients, so this brown thing and this purple thing here, and it manages to perform the QRAM operation at the logical level while querying this physical QRAM device only a polynomial number of times. So if the cost of the physical QRAM device were only polynomial in n, then the whole cost of the protocol would only be polynomial in n. So that's kind of we're really trying here to justify this overall polynomial in n cost for logical QRAM. And I'm going to get into some of the details of how this works, and then maybe at the end we can reflect on the pros and cons of this solution. But yeah, the protocol is going to be cyclic, and it has several steps. There's going to be we're going to go through each of the steps individually, but there's like a prepare, encode, distill, teleport, and update step. And to understand the essence of this idea, I think it's helpful to first review how we perform complex gates fault-tolerantly in normal quantum fault-tolerant quantum computing. So, for example, the T gate. The T gate is a non-Clifford gate. The way that we often perform the T gate in fault-tolerant quantum computing is by magic state teleportation. So we assume we prepare this encoded magic state for the T state, which we do by methods of like magic state distillation, magic state cultivation, and then we consume that state with the following gadget. We take some arbitrary state alpha, we perform an entangled measurement that produces a single bit measurement outcome m, and we observe that if m equals 0, we performed the T gate correctly onto our arbitrary state. But if m equals 1, we did not perform the T gate, we performed this other gate, the XTX gate. And therefore, when the measurement outcome is 1, we have to perform a correction, which turns out to be the phase gate in order to actually get the T gate, right? So it's an attempt at teleportation followed by a correction. And our protocol will be a similar strategy as this basic kind of magic gate teleportation for the T gate, but using a n-qubit resource state, which is just a phase state given by an equal superposition of all possible 2 to the n addresses with the -1 phase attached to those for which f of x equals 1. So this will be our resource state, and we're going to show how we use that resource state to implement the QRAM operation at the logical level. We also have to prepare this resource state. So how do we prepare it? We follow a similar kind of way of preparing T states. First, we prepare this state at the physical level rather than the logical level. And to do that, we use this physical QRAM device that we assume we have. So we do that. And we have an n-qubit physical state, right, which is, of course, prone to errors. And we need to try to protect it from errors. So the first step is to immediately encode this state into some quantum error correcting code on our general purpose fault-tolerant quantum processor. Here I've depicted for concreteness the surface code, but you could use any error correcting code. But right, so we have n qubits. We take them each to their own code block, and we encode them in parallel into n logical qubits, such that they're now protected against logical error. But we notice that, right, there's 2 places that errors can happen in this workflow. There's one place is this first step, right? The physical QRAM device has errors, so the state might have errors on it just to begin with. And secondly, the encoding is not fully fault tolerant because this single qubit is liable to error at the beginning. It's only at the end that you can kind of assume that no logical errors are happening. So this requires a third step where we distill these resource states into a high fidelity resource state. So basically, this is going to be similar to magic state distillation, where we consume many copies of a faulty state and we produce a single copy of a much higher fidelity state. Although the method for distillation is a bit different. Once we have this QRAM resource state, we're going to teleport it in a similar way as we did for T-state teleportation. We're going to take our arbitrary register of n qubits encoded in some error correcting code on which we would like to apply the QRAM operation. And then we're going to take our resource state, which is now encoded into a second set of n qubits. And we're going to perform this entangled measurement by performing CNOTs, measuring the n qubits, obtaining a measurement outcome m, which is a bit string of length n, and then observing that the operation that's been performed on the first n qubits is to apply a phase onto each bit string x, where the phase is given by f of x, XOR m. So this x, XOR m means that we flip each of the n bits in x by the random measurement outcome n. This doesn't seem like the thing we wanted to do, right? We wanted to implement x goes to -1 to the f of x, but instead we implemented this erroneous phase. So we need to fix this by kind of undoing the phase that we did and then redoing the phase that we wanted to do. So this is like, this is the analog of the correction, right? If we get the measurement outcome m equals 0, then we did the operation we wanted. But if we get a non-zero measurement outcome, then we require some kind of correction. And then the idea is to do this correction recursively, because we notice that this fix is just another phase, which has the exact same form as the original QRAM operation, but for a different data set, right? Where the data set, instead of being f, is now this like XOR of f and f of x plus m. So let's dig into that a bit more, right? We want to perform this fix-up operation given by this new data set that's related by this formula. We can just compute this thing classically. This is like a completely like classical operation. We're just updating this classical data set. So for example, if we get the measurement outcome 101, then we just plug all the x's into this formula. actually they kind of pair up, so we can like compute the data in our new data set just by going through each of the 2 to the n entries of the data and writing down this new data set in memory. So you might notice here, right, a caveat of this is that we have to update all 2 to the n entries of our data set. So there's like an exponential amount of classical computation that we have to do. This is not quantum computation. This is purely classical, but it still kind of contributes to the cost of this operation. Now there's some nuances here. We could parallelize this update, right? Where we could do it in kind of a classical circuit with order n depth. But then this order n depth circuit actually has like a lot of wires, and the total wire density is kind of much larger than that of normal RAM. So there's a discussion in the paper about like whether this update rule should be considered a complex operation or not. But it's definitely a caveat here that we need to update all of the entries in the data set. But suppose we've done that, then what we can do is we can just call the procedure recursively on the updated data set. So this is a figure that's going to depict the full distillation teleportation protocol, right? On the top register, we have the n-qubit register on which we would like to apply our logical QRAM operation. And at the bottom, we have our classical data set, F, which is 2 to the n bits. What we do is we first use this physical QRAM device to prepare a bunch of physical resource states. We encode them, and we distill them into a single high-fidelity encoded resource state. So that's what those 3 steps do there. And then we do this teleportation gadget. We retrieve a measurement outcome M, and we update our data set. That's what this yellow box is depicting, to a new data set shown here. And then we just repeat the process. We try to apply the QRAM operation for the updated data set. We get another measurement outcome, and we update that data set as well. So we keep doing this. We keep applying an operation, realizing we need to do a correction, and then trying to compute what the correction should be. And you might think we're not making any progress. Unless we get really lucky, we're just going to keep doing this over and over and over again. But it turns out that actually this process will terminate after at most n rounds. So if you keep doing this, eventually your data set will become a constant. So it's either all ones or all zeros. And when that's the case, then you don't have to do the QRAM operation anymore, because the QRAM operation is just the identity operation. So you can stop this recursion. Now, why does this happen? Why does the data set become constant? There's a couple ways to see it. One way is to it's related to this concept of the Clifford hierarchy. So the T gate is in the 3rd level of the Clifford hierarchy, and when you do a correction for the T gate, you get the S gate, which is in the 2nd level of the Clifford hierarchy. So the correction is always 1 level lower, and we can kind of prove that QRAM is in the nth level, and therefore after n rounds, we're guaranteed to be in the 0th level, which is just the identity operation. So that's one way of seeing it. But a kind of a related way is to look at this function f in terms of its expansion into monomials in its bits over the field f2. So we can always write f as a XOR of these 8 terms. And then we can look at the updated, this f of x plus m, which is also an XOR of the same 8 terms, but with different coefficients. And if we add these together, we can see that their highest degree term, the degree 3 term, is the same for both of these. So if we XOR them together, it's going to cancel out. And we conclude that the degree of the update function is always 1 smaller than the degree of the initial functions, right? So we're going to start with the degree n function by, because that's generally what we'd have. When we do this update rule, we'll get a degree n minus 1 function. When we've done the update rule n times, we're guaranteed to have a degree 0 function. What are the degree 0 functions? There's only 2 of them. It's the constant equals 1 and constant equals 0 function. That's that's the technical explanation of why this recursive protocol is guaranteed to terminate after at most n rounds.
So, quick question.
Yeah.
I guess like if your error rate was low enough, then you might in principle terminate before n rounds anyway, just because you're highly likely to succeed. Like in your correction.
I think that's a misunderstanding actually. Even if everything is perfect, you have to do the corrections, right? Because actually in this teleportation gadget.
Oh right, yes, of course they're equally likely. I see. Yeah.
The measurement outcome is equally likely, even when the resource state is perfect and everything is perfect. So this is like the cost we pay for fault tolerance.
Yeah.
Is this adaptivity? Yeah.
Okay. Success rate's like 1 on 2 to the n or so. Can I also just check if you had a error in your measurement of m, can you deal with that? Because I guess here, like, your correction is incorrect.
Yeah, I think that would kind of ruin things, as far as I could tell. But it's okay in our protocol because we've assumed here that we've already encoded everything, and so we're performing this measurement fault-tolerantly, and so we can suppress the error. We can suppress the chance of a logical measurement failure exponentially just by growing the code distance. We don't need to make the hardware any better. But yeah, of course, we need to choose the code distance big enough so that these measurement errors are low enough. But I think it would ruin the protocol if m were obtained incorrectly. Yeah. Okay. Yeah. So I guess maybe this is a checkpoint here where we have the full protocol here. We explained how we can perform the logical QRAM onto this first register. All we need is a polynomial number of calls to this physical QRAM, a polynomial number of updates, a polynomial number of encodings, encoding operations, and everything is polynomial except for this update, classical update, being kind of hiding this 2 to the n classical cost. Are there any questions about the protocol so far?
I'm gonna be a little bit annoying, so maybe not to spend too much time on this, but in the setting where we generalize f of x is a bit to f of x is k bits. Do you think this correction of this n round thing is still going to hold?
Yeah, it does still hold. It turns out that the resource states you need are okay, let's say you have k bits, as you said. The resource states become larger, so they have n plus k bits in them. Basically, you have n bits which store the address in equal superposition, and then 1 bit for each bit you want to read in. But you can construct resource states that make this work. However, the degree of the function that this corresponds to is still only n. So you don't have n plus k degrees. So you only need n rounds. Yeah, so you might worry that you would need n plus k rounds, but actually you only need n rounds.
Is this approach essentially doing a QRAM 1 for each bit, kind of separately, and then you just send the same address to all k QRAMs? I
think there's a slight there's a slight distinction there. Yeah, there's kind of 2 ways. That's one way to do it is just to treat each bit separately and read in each bit. But if you know that you want the same bit from every you want a certain address and you want all the bits of that address, it's slightly inefficient to kind of do them independently. And so you can. But you can see it because if you did k independent QRAMs, then the total address size would be n times k. But if you do kind of k at once, you can get n plus k. And there's a trick. I guess I didn't make any slides on it, and I'm trying to remember now on the fly how the resource state works. But we talk about this, I think, only in the appendix of the paper because we didn't think it was. We thought it was distracting to the notation, but yeah, I think it's an important question because normally we do care about more than 1 bit. It's true.
Okay, cool. Thank you.
Yeah. Okay. Yeah. Now I want to take a few slides to talk about step 3, which I didn't talk about very much. This distillation step. This is one of the more technical steps. But I hope to kind of get across the gist of how it works. And I'll mention here to start off, we do have to make one assumption about the way that our physical QRAM device works in order to kind of cross the T's and dot the I's for this distillation step. Although it doesn't quite feel essential, but I'll explain what it is, which is that we assume that our physical QRAM device it could have very strong noise. It could be very noisy, but this noise should be data set independent. So we're going to model this QRAM device as like a sequence of 3 operations: a noise channel, followed by the ideal noiseless QRAM operation, followed by another noise channel. And these 2 noise channels can be like, they don't have to be weak. They can be very strong noise, but they need to be independent of F. So this, no matter what function we're applying, this blue thing would depend on F, but the 2 pink clouds would not depend on F. That's the idea. And the reason we like this is because we can do twirling on this operation. And we do what we call partial Clifford twirling. So given that we're about to apply this QRAM device, we choose an n-qubit gate C at random from a subset of the Clifford group. In particular, we choose the subset that's generated by Z, X, controlled Z, and controlled X. So it's the whole Clifford group, but it doesn't have the Hadamard gate and it doesn't have the phase gate in it. So it's a subset of the Clifford group. And then what we can do is there's kind of a symmetry here where we can transform the data set into a new data set that has the property that if we prepare the resource state for the new data set and then we apply this Clifford gate, we recover the resource state for the old data set. And then rather than preparing this new resource state directly, what we do is we prepare the modified resource state and we apply this correction fault tolerantly at the end. So actually they have this circuit over here, which is like, you can kind of see here, F is entering from the bottom. First, we choose a C randomly and we're going to take the expectation over C. We modify F to some new thing, and then we query this oracle on this like physical this physical device on the updated data set, and then we apply the correction C at the end. And the important technical claim is that when we average over all the choices of C, we're guaranteed that the state we prepare, which we call this phi twirl, has the correct resource state as its principal component. Meaning that this is a mixed state because there's noise, but the largest eigenvalue, the eigenvector associated with the largest eigenvalue of this mixed state is pointing in the right direction. Basically, all of this noise kind of cancels out to like points in like a, it's sort of like depolarizing. It doesn't quite become depolarizing, but it almost becomes depolarizing in such a way that this is still pointing in the right direction. Another way of like seeing what's happening in this twirling is that like we start with this data set on the left that we want to query, but instead we choose a C randomly. So for example, here are 3 such Cs, and then we compute a new data set based on the old data set in some kind of straightforward way. And then we query the new data set instead of the old one to kind of hide from the noise which one we actually care about, and then we recover only later. So yeah, this is a kind of a technical ingredient, which in the shorter versions of this talk, I haven't been able to get into, so I was excited to be able to put a couple slides about it. But it's not that important to necessarily understand the details. And then once we have this fact, which is that the state we prepare has as its largest eigenvector the state we care about, then the distillation procedure reduces to this task of quantum purity amplification. So we have a bunch of mixed states, and we just want to purify it. We just want to prepare the largest component of it. And this is kind of a known primitive in quantum information science, how to distill, how to purify mixed states. In fact, these purification protocols, like they're agnostic to which state they're purifying. They don't care what state they're purifying. They just take as input a bunch of mixed states and produce a single pure state. Right, and this is actually a hot topic. There were 2 papers last week on quantum purity amplification. Within the last week, I think a couple of days ago, which kind of showed optimality of some generalized versions of this procedure. So this is kind of a thing that's been studied on its own right. And one of the technical contributions of our paper is actually to give an alternative method for this purity amplification procedure, which has certain pros. So I guess we can recall here from the previous slide that the goal is to turn many copies of a mixed state into a single purified copy. Relatedly, if we could just measure the state rho in the eigenbasis of rho in, we would have a reasonable chance of collapsing onto the largest eigenvector, and that would be solving the problem, right? So this begs the idea of what if we could just do phase estimation using the initial state rho in, using rho in as our Hamiltonian, right? So we're both using rho in as the initial state, and we're using rho in as the Hamiltonian on which we want to perform phase estimation. This might seem strange, like how do we actually exponentiate rho in? But it turns out you can do that. And the way you do that is with this primitive of density matrix exponentiation using quantum principal component analysis. So there have been some papers on this. And this allows us to kind of implement this Kataya version of phase estimation, at least to some quantifiable precision. There's kind of a lot of details, I guess, on how this actually works. But ultimately, we're able to distill to some error epsilon dist our pure state that we want as output, and the number of copies that we consume is goes like 1 over epsilon, and then there's some factors of f, where f is the purity at the beginning, right? So if you have a very mixed state at the beginning, obviously it's going to be harder to distill. But importantly here, we're paying as 1 over f squared, and some of the previous quantum purity amplification protocols pay as exponential in 1 over f. So this has a better procedure, a better complexity when f is small, and it actually matches or almost matches the optimal complexity, but it has the advantage over the optimal protocol in that it works in the streaming model. So what that means is it works even when you receive copies of rho in one at a time, rather than needing to receive many copies of rho in at the beginning and process them all at once. I guess just as one final slide on this, we have this phase estimation gadget, and the way this decomposes is we take this this exponential of rho in, we do kind of a decomposition of this as r small steps, and then each of the small steps is done with another gadget, which is essentially this partial swap gadget, where it's not important the details here, but you can see basically we have 1 copy of rho in coming in, and then we consume r copies of rho in along the way to kind of approximate this channel here. So yeah, this is another technical ingredient that sometimes don't get to say much about, but here gave you a flavor of it. And yeah, so that I guess if we go back real fast to the protocol, I think we talked at least a little bit about most of these steps now. I guess we didn't really talk about step 2 still, but this is kind of a purely quantum error correction question, like how to encode states. But yeah, so that kind of completes an overview, I guess, of the protocol. So I guess in the remaining time, I want to just give a few conclusions here, and then maybe we can take some questions. So yeah, the conclusion is that the protocol explains how if one had a dedicated device that could perform QRAM at the physical level, similar to classical RAM, we build classical RAM chips that are specific for performing RAM. If we had that, then we could use it to perform QRAM at the logical level. And the number of times we'd have to call that black box is only a polynomial number of times. There's no need to do quantum error correction on the individual components of the device, right? So we didn't open up the QRAM circuit and perform error correction on individual components. Rather, we kept the device as it was, and we performed error correction on the outside of the device. That's the more, we avoid needing this exponential overhead of quantum error correction. We avoid needing this 15 terabytes of syndrome data, right? So it feels much more practical, but it did come at a cost, which was the cost of this fault tolerance was the need to have this adaptive protocol where we learn these measurement outcomes, and then in the middle of the protocol, we have to replace the entire data set with a new data set. And this data set has an exponential number of entries. So if we're doing this one at a time, right, that's going to incur an exponential classical cost. Now we can still interpret this as kind of trading exponential quantum for exponential classical costs. And that It's potentially desirable because often we think classical cost is going to be less in practice by a large constant factor, but it doesn't really completely justify this cheap QRAM assumption. And in fact, it kind of exposes a way in which the cheap QRAM assumption is still in doubt. The fact that our protocol fails in this way, begs the question of whether that's necessary. So I think kind of an important pressing question for the future is, can we relax this? Can we reduce this need for exponential classical cost and give a more complete justification of this cheap QRAM assumption? There's some other questions, such as like this distillation approach is kind of stupid. It doesn't use any information about QRAM. It would work with any state. It doesn't use the fact that the state we're trying to distill is a state that we know, which is this QRAM resource state. So could we come up with better ways that have lower overhead that could make this more reasonable in practice? And yeah, like could we relax this assumption on the noise? And can we, try to understand if this could actually be applicable in some real applications? So those are some of the topics for future work. And yeah, just remind everyone this was joint work with a number of other folks. And yeah, thanks for your attention, and happy to use the rest of the time for questions.
Right. Thank you very much for a very wonderful talk. Yeah, I think like there was already some discussion during the talk itself, but if anyone was kind of like delaying their question until this point, please feel free to unmute yourself and ask now.
Can I just kick off with a question? Maybe it's more of a clarification than a question. So like, it seems like, maybe I don't fully understood this point, but it seems like you're kind of talking about these corrections that you do as, requiring a kind of update of your entire like RAM data to do the correction, because you're kind of rewiring the addresses. Isn't your twirling step a kind of more complex version of the rewiring? Because if you did a twirl just with X's or something, you're rewiring, right? So how is it that you can do the twirl but not the...
Okay, yeah, good point. You're exactly correct. The twirling step also requires that we replace the whole data set. So this and indeed it's a bit more complex, because computing the new function from the old function and this C is going to be, it's still not that hard, but it's going to be a bit more complex. So yeah, I think I did brush that under the rug a little bit, and I think the reason is that the twirling is not, it was like a hacky solution that we did to kind of make this distillation work, but it might not be needed in practice if it turns out that you have this principal component fact is like already true or already approximately true, and it's just the update step is much more essential to the protocol. Like even if you have perfect resource states, you still have to do the update step, and so that feels like inevitable. Whereas the twirling, it's also there, but maybe you wouldn't actually have to do it in practice depending on how this evolves. But I think it's a good point. And in the paper, yeah, we do, polynomial number of updates, polynomial number of twirling updates. Yeah, still only 2 to the n, not like a bigger exponential. Yeah.
Okay, cool. Okay, maybe if there's no one's asking a question, or while they're thinking, I'll ask another one. So it seems like in the purity amplification step, you're basically just measuring in the eigenbases, and you're saying that like if my eigenvalue is larger than some cutoff that I know is only possessed by the largest eigenvalue, then I'll keep it and I've purified. And otherwise, I'm just going to try again. Is that right? Is that the basic idea?
Yeah, that's the basic idea. Yeah, so we're assuming that one of the eigenvalues is like of size f, and the rest of them have to be like a constant factor smaller than f, so that there's a gap.
Yep.
Actually, if you buy the twirling, like if you're willing to do the twirling, you can guarantee that like one of them is f, and the rest of them are like 1/2 to the n. So actually, they're like quite small and like all the same.
Okay.
So
But
yeah, so there's a big gap.
But I guess you have to know what the cutoff is so that you can say, oh, I've definitely got the principal component. Because otherwise you could make the mistake and get like the second principal eigenvector, and then you claim that you've purified, but you haven't.
Yeah. I guess there's a question here. Do you have to know what f is before? I think we kind of assumed you knew what f was most of the time, but it doesn't feel like a fundamental problem. I think you could like start by guessing like a large value for f, and then if it does, like you should know when it fails. Like you do the phase estimation, you like can like learn the value of the eigenvalue, and if it you know, if you thought f was large, you would learn that it's, you know, that was wrong, and you could like decrease your guess for f. I think you could solve this problem. But it is true. Yeah, that somehow you do need knowledge of f.
Okay, cool.
Right?
Hello. Thank you for the presentation. I have a question about the outputs there. How do you generalize it to like to output like more than 1 qubits here? Because the distillation protocol, you need to encode the f of x in terms of the sign, right? So I'm not sure how to generalize it to multiple qubits.
Yeah, so there's a way of generalizing it. Let's see. So I think it's equivalent to the following. If you take a equal, so let's look at this. Okay, if I take an equal superposition of all the x's, forget the sign, and then I attach to it f of x in the stored as a classical vector. I mean a classical bit string. So it's a sum of all the x's of x f of x. It's like an n plus k qubit register, and then I apply a Hadamard on all of the k other bits. So now, like Hadamard maps 0 to 0 plus 1, and it maps 1 to 0 minus 1. So then you're left with an equal superposition over all 2 to the n plus k bit strings with a sign. And the sign is now dependent both on x and on like the value in the k qubits. So basically you can recover a state of this form for the case where there's multiple output qubits. Instead of having n qubits, it's n plus k. Yeah, but the protocol still works, and it only needs n rounds, or might be n plus 1 rounds. Yeah, the appendix of the paper I think explains this more clearly, probably. Does that help?
Oh yeah, I think so. Yeah, I think so. I mean,
I might ask just one more question. Like, so I guess like the big difference between these like purity amplification protocols and something like magic state distillation is you know, with distillation, you kind of know the target state, and then you can get to it exponentially in the number of rounds. Whereas with these amplification methods, it's agnostic to what you're trying to purify, but now you have to do like a one on poly kind of rate of convergence to purity. So like you can get a drastic improvement in the rate of convergence if you could maybe find, like construct some, like now you need like you got to use these like code methods that they use for like distillation, and now these codes depend on the data set that you're trying to purify. But you can imagine you could do something like this and then get lift up your convergence rate from like 1 on poly to 1 on X. And what would that buy you if you did that?
Yeah, so this this expression here is the like overhead, the number of copies that you need to produce a copy that is like epsilon dist, correct? And right, so epsilon dist is like the logical error. So we want that to be really small. If we're calling QRAM like 1,000 times during our algorithm, we'll need to make epsilon dist like 1 over 1,000, and then we're paying this 1 over epsilon cost, so that's like multiplying by 1,000. So if instead we had a overhead that was like log 1 over epsilon, which is what you get when you do like T-state distillation, then it would be many fewer copies. It's still polynomial in the sense that like epsilon is never smaller than 1 over poly n, but in practice it's like a huge factor.
But
so
yeah,
I think
it doesn't like completely change the protocol, right? It's not like you still, it's just a constant overhead thing, which is a big deal, but it's not. It doesn't like suddenly change the regime into something very different. Is that right?
Yeah. So I think if you're trying to just justify the cheap QRAM assumption and all you care about is like polynomial and n cost, then it's not important to like seek better distillation protocols. The one that we supplied is like already good enough. But if you want something that's actually applicable, then I think it is a good idea to try to find better distillation protocols. And in particular, I would say, I mentioned these applications where cheap QRAM is necessary. And if you have it, you might have an exponential speed up. And then I mentioned these other applications where cheap QRAM is not necessary. We're already paying the exponential cost, and we would just like to improve it. These are the applications where if you had a better distillation method, then it could be plausible that our protocol could actually be useful for like speeding up chemistry and speeding up Shor's algorithm. Because we know in those applications, like the exponential classical cost is like already something we're paying. So we don't really care about that big caveat. But when we actually plug in the numbers here, we did that in one section of the paper, like the 1 over epsilon overhead is just a killer for the actual numbers. So T-state distillation is almost always going to like be better. So I think it is an important question.
All right. Maybe one quick question or comment from anyone else, or even from Jakob. Okay, I just have a quick question about, so you have this assumption of the noise that's independent of the data set. I guess this is not really like a strong assumption in any way. I just want to get a sense of how strong.
Yeah. So you can kind of try to justify this assumption by looking at the way that we imagine doing QRAM at the physical level, which is like, you can kind of see it here in this circuit for QRAM. Essentially, there's a tree. Like the way we normally think of it is we place the data items at the leaves of a tree. So there's exponential number of leaves, and there's the depth of the tree is only n. And then what RAM or QRAM does is it like starts at the root and it like follows one path down to the leaf. It reads in the data stored at that leaf, and then it travels back up the tree to the root. And you can see that like the routing and the unrouting are both independent of the data set. They don't, if you change the data, you don't change that part of the protocol. The only part of the protocol that changes is like the read step. And the read step is really simple. It just like happens in parallel on like all of the leaves at the same time. In this circuit, like all of this is routing, and then the read is just this like one layer of X gates. So it's like reasonable to think that, if you could just do this one step in a dataset independent way, then the whole thing might be dataset independent. So I think it's a reasonable assumption. I think it could use more justification. I think it would be nice to have like a microscopic error model that, and like a concrete implementation with a microscopic error model, and show that this assumption like bears true for that microscopic error model. But that wasn't something that we included in the paper. So, yeah.
All right. Yeah, I was just curious whether, like, if you knew that it was not dataset independent, like, could you do something extra? You introduce the noise yourself and make it kind of like dataset independent.
Yeah. I mean, yeah, I did think about this a little bit. Like one thing you could just like, you could take a random, you could like add a random data set to your data set, and then like query like 2 data sets in a row such that their sum was the data set you cared about, but each one individually looked completely random. It's like a form of twirling, maybe. Like there's stuff you can play around with. I actually, like, I had an idea for like a kind of a complex version of this distillation, which could avoid having to make this assumption, where like it would alternate between doing some of this like state agnostic distillation, and then it would do some like recurse on itself and do some teleportation, because like teleportation kind of naturally decoheres some of the errors. But it seemed like it was gonna be really complicated, so we didn't work that out for the paper. But it's, yeah, I think I'm not that worried about this, because I think that there could be ways around it.
Yeah, it's probably not the most crucial thing.
Yeah.
All right. Okay. So I think, like, yeah, Hakov, you have something?
Oh, sorry. I just had a follow-up comment on this, which was, yeah, I don't know how much, like, could you also think of, like, if the noise is dataset dependent, could it also just be equivalent to like a dataset dependent noise acting on a different data set? Like these two things end up being the same, because it's like, for example, if you had like a bit flip happens if the bit is 1 but not if the bit is 0, then that's just the same as the data is 0, and it's a weird model to have a data set dependent noise.
Yeah.
I don't know what the conclusion is.
Yeah, I think that there could be some data set independent noise, like some forms of noise which are on their face like data set dependent, but then there's some simple method that works for that noise, like that noise channel to kind of, like you could just flip all the bits with 1/2 probability or something, and then the half chance there are 1, half chance there is 0, and so you kind of symmetrize this noise channel. But you could also imagine like some kind of extremely adversarial noise channel which like attacks knows what the data set is and like attacks it in like some data set specific way, and it's unclear how to come up with this general way. Yeah. Well, I think there might be there might be a hope, but not with this twirling